तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In today's experimental setup, we will be learning something about simulation. First, how a second order differential equation can be simulated, and how an inductor can be simulated, and how a negative resistance can be simulated, etc. Let us therefore see this circuit with which we have already become familiar. This circuit, which is put within this red dotted line, is called the gyrator. That is, if this is V naught 1, for example, V naught 2 is going to be twice V naught 1, okay, and here we will get V naught 1 minus V naught 1 by SCR, that is what is simulated, and from here to here, therefore, the voltage is going to be V naught 1 minus V naught 1, V naught 1 gets plus V naught 1 by SCR, that is the voltage V naught 1 by SCR, and therefore, this will be V naught 1 by SCR divided by R, which means it will give you a current of V naught by SCR squared, which means the current in this is going to be determined by SCR squared impedance, okay, which is nothing but an inductor L equal to CR squared. So, this simulates an inductor L equal to CR squared. C in this case is 0.1 microfarad, R is equal to 10 K. Okay. So, it will now simulate an inductor L equal to 10 to power minus 7 into R squared 10 to power 8, which is actually speaking 10 Henries. Okay. 10 Henries of inductor is simulated from here to ground. That is therefore going to be having an capacitor across it. So, you have an L which is 10 Henries from here to ground, and then we will put that L that is simulated by this circuit, and a C across it. This is called a tank circuit. And then if I connect a resistance R times Q, R is the 10 K resistance that has been used here, here it is Q times R if I use. This is really a tank circuit with L, C and R, okay, and therefore, its transfer function from V naught 1 by V naught V I is going to be S by omega naught Q plus S squared by omega naught squared plus S by omega naught Q plus 1. Okay. If I take the output at V naught 2, it will be twice V naught 1, and omega naught is going to be 1 over R, which is 10 to power 4 into C, which is 0.1 microfarad. It is 10 to power 3 radians per second, okay, and Q is equal to 10. So, this is going to be a band pass filter, band pass filter, because of S coming in the numerator. At omega equal to 0, it is 0, at omega equal to infinity, it is 0 because of the double pole here. Okay. So, there is a frequency omega naught at which it will peak. So, if you obtain the response of this at omega naught, it will peak, and the bandwidth is going to be omega naught by Q. In this case 10, therefore, omega naught by 10 is the bandwidth. This we will see in the experiment. if I take the output here, the peak gain here is going to be 2, because at band pass at omega naught, the gain of V naught 1 by V I is going to be 1 and V naught 2 by V naught 1 is going to be 2. So, this is going to be 2. Not only that, if I plot the phase shift, okay, initially phase shift is due to only S, that means 90 degrees, and then the phase shift is going to become 0 at omega naught and goes to minus 90 degrees at very high frequencies. So, phase shift also is going to 0 at omega naught. So, this is the characteristic of a band pass filter. Magnitude will peak at this and phase shift will become 0 at omega naught. Both of this and phase variation is maximum around omega naught. Okay. So, this particular aspect of the experiment we are going to see just now. You can see that this circuit has been built there, and Devaki is going to now demonstrate the fact that the output by input is equal to 2. You can see the lower one is the output, upper one is the input. Output by input is equal to 2 exactly at omega naught, which is roughly 10 to the power 3 radians per second, or is equal to about 200 hertz. Okay. So, you can see this as she varies that frequency, you can see on either side of this it is decreasing. That is why see, it is decreasing on one side, now you increase, yeah, it is peaking. Again she is changing in the same direction and it is decreasing on the other side also. Okay. So, that is why it is going to give maximum gain at center frequency. Now, she will also show you V naught versus V I. This is V naught versus time, V naught and V I versus time. Now, she will show V naught versus V I, which will be giving you the phase shift between output and input. This is an ellipse because of a finite phase shift, and phase shift changes, and phase shift becomes equal to 0, 0 means it is a line, and on either side of center frequency it will become an ellipse. Now, let it change from it has become an ellipse on one side and also has become an ellipse on the other side. See. So, there is a phase shift which is very nearly going to become equal to 90 degrees. As it becomes 90 degrees, go for still higher frequency, it will become almost a vertical ellipse. Okay? Yeah. So, this is a very at infinite frequency only it will become exactly 90. See? So, it becomes a vertical ellipse. Okay? So, this is the characteristic feature of a band pass filter, active RC filter, where inductor has been simulated. We had just seen how the inductor simulated can be used for a band pass filter. Now, we will illustrate how an oscillator can be made out of it. The inductor that is simulated, L is equal to CR squared, is obtained from this gyrator. Now, if I put a capacitor, it is an LC network. So, it should be possible for me to get oscillation omega naught equal to 1 over RC, 1 over root LC, which is 1 over root LC. L is equal to CR squared. So, it is 1 over RC. At this frequency it should oscillate. Now, that is really at 1000 radians per second. So, which is around 185 or 90 hertz. So, but it does not oscillate. Why? That is because the op amps are not ideal, and therefore, there is some amount of positive loss, that is resistance across this, that is why it does not oscillate. So, I have to simulate a negative resistance across it. How do I simulate a negative resistance? We have V naught 1 here and V naught 2 is equal to twice V naught 1. So, if I put an RP here, the current will be V naught 1 minus twice V naught 1 by RP. That means, from here to ground we have minus RP getting simulated. Current will be V naught 1 minus twice V naught 1 by RP, which is minus RP is the effective resistance from here to ground. So, across this inductor you have a negative resistance that is simulated. We make it variable, start from a very large value, keep on decreasing it such that at a certain value it equals the loss component across the inductor. So, this is going to be demonstrated, and at that point without anything being connected, suddenly output of this op amp will have a sine wave generated, okay, at this frequency around 200 hertz. So, this is going to be very clearly demonstrated by Devaki now. She has put across this op amp, first op amp, a resistance, variable resistance, and she will now show you by varying that resistance. Okay. So, you can concentrate on the screen. Yeah. Now, it is oscillating. If the resistance is increased further, it stops abruptly oscillating. Okay. Again change, if she increases is too much, you will see that it will get saturated. Okay. So, the resistance, if the value is decreased too much, it is going to get saturated. Okay. And now, you can see that this frequency can be determined by what is called as again plotting. One frequency waveform is applied to x, another frequency waveform is applied to y. Then you get a Lissajous figure. If the two frequencies are one and the same, then it should be an ellipse, okay? And that ellipse is moving like that because we can never make the frequencies exactly same, and therefore, there is some phase shift keeping on changing. That is why that ellipse is changing that way. Devaki, please adjust it so that ellipse becomes at least stable, okay, for some moment. There you see, there. I mean, it is very difficult because both are unstable frequencies, and therefore, okay, it becomes stable for a very short amount of time. Now, she will apply double the frequency, okay, and you will see that that figure becomes unstable, and at a certain frequency you will get a figure of 8. Double the frequency means around, okay, 360 around that. Please adjust slowly. 360, 390. There. Yeah, just you concentrate there. You are going to get with is there you are, right. So, figure of 8. So, that corresponds to, okay, double the frequency. At half the frequency, again you get a figure of 8 in the vertical direction, half the frequency. Ellipse again. This is a technique of measurement of frequency, okay, obtaining this Lissajous figure it is called. Given a standard frequency input, you can obtain this kind of Lissajous figure and estimate the frequency very accurately. It is not in that, there you have a vertical figure of 8, yeah, there you are, okay, vertical figure of 8. This is half the frequency. So, you can therefore measure the frequency of oscillation by using this Lissajous figure. We now go into another filter which is very important block, which I have also explained as a universal active filter, which uses two integrators, okay, in a loop. It is also called double integrator loop or biquad, okay, KHN network it is called. Only difference between KHN network and this circuit that I am demonstrating here is that in our KHN network we had these two integrators and the inverter, and then output from here was directly attenuated and fed to the inverting terminal. Here on the other hand, this output is attenuated of course, but using an op amp, but since it is getting an inversion here, we can directly use it at the inverting terminal of this, so as to give the required negative feedback. Okay. So, instead of an attenuator coming and feeding it to the positive terminal, I am having an inverter with attenuation of course. You can see 10K and 100K. So, it is attenuation not amplification, and that Q determining network comes as a feedback factor in the negative feedback, but negative terminal. Okay. Thereby, I can use only the inverting amplifiers all throughout. So, this modifies the circuit in the following manner. If V naught 1 is this input, this is V naught 1 minus V naught 1 by SCR. Okay. Again this is integrating second time plus V naught 1 by SCR squared is what appears here. This V naught 1 is going to be amplified by 1 over Q, it is attenuated really, into SCR with a minus sign, and therefore, this becomes plus V naught 1 by SCRQ, and then this Vi is coming as minus Vi 10K 10K, and therefore, minus Vi. So, this is again inverted and is going to appear here as minus V naught 1 SCRQ plus Vi, and from here we have V naught 1 by SCR squared. So, this is what is going to be the equation for deriving the transfer function. So, from this you can note that V naught 1 into 1 plus V naught 1 plus 1 over SCRQ, this one, plus 1 over SCR squared is equal to Vi. So, V naught 1 by Vi, for example, can be written as S squared by omega naught squared plus S by omega naught Q plus 1. Okay. In the numerator, we will be having S squared by omega naught squared. If it is V naught 1, okay, it will be S squared by omega naught squared. You can see that. Okay. This actually has been multiplied by S squared by omega naught squared throughout. So, it is high pass. This is the high pass output, like in the case of KHN network, high pass. Okay. If I now use this, at this point it will be V naught 2 or V naught 3 over Vi, which is going to be multiplied by minus S by omega naught. So, this will get cancelled and we will get S by omega naught. Okay. That is band pass at this point. Again it is going to be multiplied by omega naught by S minus, and therefore, at this point it will be low pass. This numerator will change to 1, okay, by that. That will be V naught 2 by Vi. On the other hand, if you take this, this will be a notch output or band elimination output, wherein it will be having S squared by omega naught squared plus 1 as its function. Okay. So, this is going to be band elimination at this point, low pass, band pass and high pass here. So, this is able to give all important outputs. Very nice demonstration of what exactly happens in this circuit can be given by feeding Vi as a square wave. So, that is depicted here in this. This is the square wave at a certain frequency, omega equal to determined by the time period here. Okay. And if it is exactly tuned to omega naught, if the incoming frequency is same as omega naught, which is equal to 1 over RC of the filter, then at the band pass output it should give me the fundamental. You should select the fundamental and eliminate all the harmonics. So, this may be some kind of fundamental output, okay. And it will be almost Q times the input. Okay. So, the fundamental amplitude will be very huge. Okay. If I apply some value of input signal, Q times that is going to be the fundamental output, okay, compared to the fundamental of the input square wave. Now, if I see the notch output or band elimination output, this fundamental is going to be eliminated from that if it is exactly tuned to omega naught, and you will see that from the square wave I am removing the fundamental. If you remove this fundamental as this thing, you are subtracting and you will get a waveform which is containing only third harmonics and higher harmonics. You can see that it is third harmonic because in one time period, okay, you have 1, 2, 3, okay, and 1, 2, 3. Okay. So, it is predominantly third harmonic and higher, because these are not exactly sine wave. So, higher harmonics are also present. This is going to be demonstrated clearly to you. This is a high Q circuit. I have purposely made this Q pretty high here. Instead of using 10 K, if I use for example 1 K here, this input is going to be also attenuated by 1 over 10 here, but Q is going to be 100. So, we have designed it for a Q of 100, and therefore, here input attenuation is 1 over 10 instead of 1 of the earlier situation. This is going to be demonstrated by Devaki. She has built this entire circuit, and now you are going to see the square wave that is applied at the input. Please, that is the input square wave, for which she has shown you the output of the band pass, which is nothing but the fundamental, which is amplified Q times compared to the fundamental of the square wave. Please do the tuning and see that it rapidly falls. See, yes, concentrate on the screen, it rapidly falls, and again change. This is the center frequency. On the other side also it rapidly falls. See, it rapidly falls. Again tune it, please, exactly, tune it exactly to the center frequency, so that you get the highest fundamental output. Now, let her show you the notch output. The fundamental has been eliminated, so only the harmonic should be there. Their output amplitude should be extremely small, and therefore, she is changing the scale so that the small amplitude of the harmonic content can be shown to you at the output of the notch, and you can see that waveform exactly as I had shown you on the board. Now, please tune the thing so that it is exact. See, tuning, that is what is called tuning exactly, because now it clearly tells you how to do the tuning. Those two peaks should be symmetric with respect to the center point valley. That is the board waveform, and you can see exactly the same waveform being shown there. This is the case only if the square waveform is same as the omega naught. If it is different, you will see that the output is going to be a square wave if the input is a square wave. Please show the thing, change the frequency. Now, so the output is simply the square wave. On either side of omega naught, output of the notch is a square wave, right. So, it has not eliminated anything at all, and therefore, output is simply a square wave for an input which is a square wave. This is a notch filter. This is going to be really tuned only when it is tuned exactly to the omega naught of the filter, it will remove the fundamental and not otherwise. This is the use of the, please tune it exactly, because do not leave it. You can see she has real difficulty in tuning it exactly, because the Q is very high and it is test oscillator. Yes, thank you. I have to make only one comment. Last time when we saw the notch output, the notch output that we saw on demonstration has a phase inversion of 180 degrees. What I have drawn is without phase inversion, when from the fundamental, from the square wave, fundamental is removed, what is shown is going to be the notch output without phase inversion. So, with phase inversion is what you really saw on the screen of your oscilloscope. Now, I am demonstrating here another experiment using the same block. We had this part giving negative feedback, and Q here has been adjusted to be 10, brought back to 10 from 100, 10 K, 100 K. So, I put 100 K variable resistance here, so that Q can be made infinity. From here to here there is negative feedback if it is fed this way, but from this to this it is directly getting fed without going through the inverter. That means, it is going to introduce positive feedback. So, if I put 100 K resistance around 100 K, it should be capable of changing the Q to infinity, because there is a positive Q of 10. Okay. This will introduce positive feedback such that the Q can be made equal to infinity. At that point it will go into oscillation. This is called quadrature oscillator. Why? It is using double integrator, and if you take the output from here to here, frequency of oscillation is going to be 1 over RC, which is 1000 radians per second as usual, okay, if it oscillates. And when it oscillates, okay, this amplitude is going to be same as this amplitude, okay, but phase difference of 90 degree is going to be seen between these two outputs. That is why it is called quadrature oscillator. The phase shift is 90 degree. So, it is quite useful in communication, okay, where you want to generate two outputs in quadrature. Okay. This can be seen now. She has assembled the same circuit now, and it is oscillating there. You can see the screen. Okay. Now, the please change the feedback so that it stops oscillating. It stops oscillating because she has introduced more negative feedback than positive feedback. Now, introduce positive feedback, so it starts oscillating. Yes. Now, and it is almost going to saturation, you can see. Okay. There is no control over amplitude of oscillation. It will go to almost plus minus supply voltage, you can see. See, it has gone almost up to plus minus. She has introduced too much positive feedback here. Okay, now it has gone to saturation altogether. Too much of positive feedback. And this is clearly demonstrating the effect of too much of positive feedback. You have to just introduce positive feedback in order to get rid of the negative feedback. Then only it will give you a perfect sinusoid. Okay, otherwise it will be distorted. Now, the frequency of oscillation is once again around 200 hertz. Now, I want you to see the phase difference between one output and the other output. Will you please connect another output, okay, so that they can see the phase difference between one output and the other output. She is now connecting another output, so that you can see the effect of quadrature, that is phase shift of 90 degree between the two outputs. So, this is perfect circle, you can see, because amplitudes are same and there is a phase shift of 90 degree, and it is a perfect circle, okay, x squared plus y squared. See, she is changing the feedback, so the amplitude changes slightly, but it is vanishing, and when it is growing, both are growing simultaneously. That is perfect quadrature, okay, output. This is the beauty of the quadrature oscillator. Thank you. On demonstration of negative feedback and positive feedback effect of this, we have clearly brought out filters, oscillators, etc. Now, we will see how certain amount of nonlinearity can be got rid of, okay, by using negative feedback. This is precision rectifier, its application, and elimination of crossover distortion in class B power amplifiers. This can be done with the help of negative feedback. How do we do that? Let us see here. I am explaining about the precision rectifier, which we had earlier discussed. Okay. This contains the op amp here, and this converts the voltage into current. So, whether it is going positive or negative, this is converted into current, which is V I by 10 k, and V I by 10 k always flows through this. But on the output side, this V I by 10 k is pumped into this diode, okay, when it is going positive, and if you do not have anything else connected, right, then this is eliminated, this path is eliminated, and therefore, this current cannot go anywhere. Okay. So, the op amp is going to behave like a comparator there, where it will be simply magnifying whatever voltage is appearing here at this point, but that is of no use, because this positive voltage is going to get converted into negative here, okay, and this diode is going to conduct. But when it goes negative, okay, this is going to be having open loop. If you do not have this conducting, this will be open loop, and this voltage will appear here, okay, and this voltage will appear here as well, right. So, when it goes negative, this voltage, input voltage will appear here. When it goes positive, this is going to be inverted. Therefore, with the resultant effect, you see a waveform like this. When the input goes positive, it will be inverted because both resistances are equal, okay. If this is plus minus, this is plus minus. So, this is at ground potential, and therefore, this is inverted and appears as minus V p, and this appears as such, okay, because the op amp has no feedback at that point. So, you get a full wave rectified waveform, but that is no use because the moment I load this, okay, this voltage waveform is going to change its shape. So, this depends upon the load here, but I want the output to be independent of load. So, what I do is when it goes negative, I will permit a path here, so that there is going to be another diode connected to take that negative current, okay. But at that time this voltage is going to be virtual ground. So, this voltage is transmitted here as virtual ground. So, it will clamp to ground potential. So, this output here is going to be a true half wave rectifier only if I connect another diode, okay. So, we will see the demonstration even if this is not connected purposely to see whether we get this waveform, and you will see that this amplitude is different from this, okay. It depends upon the amount of loading it has. I am connecting an oscilloscope here and all that, even that may load to a certain extent this, okay. This waveform is seen, then moment this is shorted, you will see that this is clamped to 0, okay. This demonstration occurs, and this is independent of the cut in voltage of the diode, okay. As soon as this goes positive, this will try to go to negative saturation. So, the diode conducts as soon as this voltage goes to minus V gamma. So, this actually voltage jumps from plus V gamma to minus V gamma. You will see this waveform also, okay. So, the op amp comes into picture, jumps to plus V gamma and minus V gamma respectively, so as to make these diodes conduct, okay. That is why the conduction of the diode is independent of its cut in voltage as long as the gain of the amplifier is very high, and therefore, we are able to use a practical diode in the negative feedback path and get a rectifier which can rectify even millivolts of peak input voltage. So, this demonstration is going to be done there, you can see, right. The circuit has been built and constructed, and now what you are going to see on the oscilloscope is a situation where the other diode is not connected. You can see that the waveform is there, but it is showing full wave output, okay, instead of the expected half wave. Now, she will connect the other diode, and you can see that output is going to be clamped to 0 when the other diode is not conducting, right. So, you can see that this is a half wave rectified waveform. Devaki, you can show the other output also here, because that also is the other half wave, okay. Each of these will give you half wave. This is one half wave, okay. This is the other half wave, okay, at the end of the other 10K, okay. So, you can see now this is going positive, other one was going negative. So, you can get two half wave rectified waveforms here clearly, and if you now see the output of the op amp, please show the output of the op amp. So, output of the op amp, you can see it is jumping and then, okay, following the input. So, it is jumping by an extent equal to V gamma, plus V gamma and minus V gamma, and trying to follow the input. So, even if the input is very low, make the input low, you can see that it is almost becoming a square wave, increase the triggering. So, input is very low now, okay. It is less than cut in voltage of the transistor, and further reduce the input, go to the higher range, yes. and slightly right. You can see here clearly input is very low and output of the op amp is almost looking like a square wave, whereas the diode is still rectifying. Half wave rectifier output, please show. Scale. Yes. See, you can see the thing is still faithfully doing. What is the input level, please? 10? 150 millivolts, okay, and even so output is going to be half wave rectified. So, this is the precision rectifier. Let us now see the board, and in the case of class B power amplifier, the same scheme is going to work, right, but it is going to be a power amplifier application, right. It is the same as that of the diode scheme, right. Okay. So, you can see that this is the class B power amplifier, 10K 10K we can put, and there is a diode, okay, connected like this here and like that there. Okay. So, as far as the current is concerned, current is always going to flow in this direction. So, when it is flowing here this way, okay, this transistor will take that current. When it is flowing in the opposite direction, okay, it is this transistor which will conduct. Okay. So, it is equivalent to the same circuit, only thing is we have R and two diodes connected in parallel, right. But the current taken is actually, as far as the op amp is concerned, it has to feed only the base current in order to retain the transistor in conduction. So, the basic principle of this structure is exactly similar to what we have just now demonstrated of the precision rectifier. So, if you see the waveform at the output of the op amp, it will be again a square wave like thing, right, and here it will be absolutely a sine wave, even if the sine wave amplitude is going to be very small. Okay. This is going to be inverted here and going to appear here as a perfect sine wave in spite of the diodes conducting only after cut in voltage is applied. Okay. So, this is clearly demonstrated in the case of precision rectifier as well. Now, we will demonstrate certain applications of the multiplier, which we have also studied in our theory class. If Vx is one input and Vy is the other input, output is Vx Vy by 10. In the case of an ideal multiplier, Vx and Vy both will have a dynamic range of plus minus 10 volts. Now, if Vx is, let us say, some frequency input, let us say we will say that it is Vp sin omega Ct, the carrier, right, and Vy is, okay, the modulating frequency, okay, omega m. Let us say omega c is some 1 kilohertz, okay, and omega m is 100 hertz. Right. So, we have this gain being changed by the modulating frequency, gain of this amplifier. In fact, we can see that this is Vy, okay, by 10. You can consider the lower frequency one as the gain, Vy by 10 is the gain of this, and Vx is the amplitude which is Vp sin omega t. So, Vy by 10, that is the gain is changed for this Vp sin omega Ct. So, when Vy is high, the gain is going to be high. When Vy is low, almost 0, let us say it goes to, gain is going to be 0. Okay. So, this is something like frequency shift keying. There is going to be the carrier frequency information coming for some time and not coming for some other time. This is going to be demonstrated now by Devaki there. on the screen you can now see she has connected a multiplier input. One input corresponds to modulating frequency of 100 hertz, another corresponds to the carrier which can be varied of course, is about kept at about 1 kilohertz, and you can see the lower one corresponds to the carrier, the upper one is the output of the multiplier, and since these frequencies are not very stable, okay, it can be triggering only one waveform properly. We see that kind of movement there, and it is the modulated output. Please vary the modulating frequency now from 100 to 50 or something, right. So, she has changed the modulating frequency from 100 to 50 hertz, and now you can see again the modulated output. See, the frequency is different. So, gain is made very nearly equal to 0, nothing of the output is visible there, and output is fully visible during other. So, it is a square wave modulation. Okay. So, this is a clear application of multiplier. In the last demonstration you saw the gain was varying from 0 to 1, 0 at some interval and 1, it is called frequency keying, right. Now, if you want to convert this into AM, amplitude modulation, you have to make it non-ideal. We want the gain to vary from some value to some other value. That means, we have to apply a DC, okay, plus the modulating frequency. The DC will bring the carrier and the modulating frequency will change the amplitude from some value to some other value. Okay. So, we have now had an arrangement where we have added the DC and the square wave at 100 hertz. So, that output is an AM. Now, that is demonstrated to you by Devaki again, okay, clearly bringing in a DC, yeah, and an AM. Now, let us concentrate on the screen. The output of the multiplier corresponds to the amplitude modulated output. Okay. You can see the amplitude modulated output here. Okay. Please go to another lower frequencies range, please. You can concentrate on the screen meanwhile. Yeah. So, you can see the amplitude modulation here, it is going from the maximum to minimum, okay, abruptly, because it is a square wave. Now, what we are doing is we are doing synchronous detection. The output of the modulator is fed to another multiplier, okay, and this is now fed to sort of low pass filter, so as to eliminate the high frequency component, and you can see this, the output of the multiplier now contains carrier also before filtering. Okay. You can see the square wave, okay, and then the filtered output. Filtered output, this is the filtered output. Increase the scale please for the filtered output. Yeah. So, you can see still it is only a low pass filter that has been put. So, the carrier is still there. Okay. If you want better filtering, you have to put higher order filters, so that you can get this square wave back. This is the demodulated output. This demonstrates synchronous demodulation. Okay. This is not normally adopted. What is done is envelope detection, okay, because it requires the presence of carrier to multiply with the modulated waveform in order to get the output. So, this part of the experiment demonstrates some of the communication applications of the multiplier. Now, we will demonstrate another application of the multiplier wherein same input is fed to both the Vx and Vy, Vp sin omega t, Vp sin omega t. Output will be Vp squared sin squared omega t divided by 10, which means it will have a DC component and a 2 omega t component. This is going to be therefore its application as frequency multiplier. So, if you feed omega, you get 2 omega as the output. This is demonstrated very clearly now by feeding the two inputs to this multiplier, same input to the multiplier, and you can see here for one cycle of the input waveform, which is shown at the bottom, you have 2 cycles of the output waveform. You can clearly see that there is a certain amount of feed through component of the fundamental, that is the omega component coming, because the multiplier has a certain amount of offset. So, the feed through component also is coming along with the doubled frequency component. So, this can be eliminated by adjusting the DC applied to one of the inputs, so that the feed through component gets cancelled. Okay. So, this gives you frequency doubling effect, and we can multiply frequency by using successive multipliers, okay, and we can generate a periodic waveform this way.